G'day viewers. In this segment we're going to talk about the uses of networks. These are important to understand because they tell us the advantages of networks as well as what the network needs to do well to support its different applications. Now, as you can see, we use the internet in all sorts of contexts: at work, at home, and on the go. At work, you might use the internet for email, different kinds of file sharing, printing, and so forth. At home, often to watch different kinds of media, movies or songs, as well as the news, different web applications, including e-commerce. And while mobile, you continue to use the internet, not only for making calls and sending messages, but also for playing games, accessing information, including playing videos, using different sensors such as location and maps and so forth. I'm sure you're familiar with many of these applications. The key question for us is what all of these different uses of networks tell us about why we build networks. This is important to understand because it lets us know what a network needs to be good at and what the key advantages are. Okay, so just going through some of the advantages of networks, the reasons why we build them. One of the first things that probably comes to mind is for communication between different users. This is the traditional use of the network from the get-go. Today, we use the network for still telephone-like calls in the form of voice over IP, for video conferencing, different kinds of instant messaging and social networking applications. Really, the network here is enabling remote communication and between two users. And one point that I'll make is that if that communication is interactive, the network needs to provide low latency for it to work well. A second key reason for building networks is for resource sharing. A network allows many different users to access the same underlying resource. Now, that resource could be pretty much anything. It could be the latest 3D printer, a search index that's been built up, or different machines, computers in the cloud which are performing computations. The key idea is that it's more cost-effective to have many users share one underlying resource than to have a dedicated resource for every user. Imagine buying a printer for everyone who wanted to print occasionally. In fact, in a network, even the network links, the bandwidth of the network, is shared via an arrangement called statistical multiplexing, which I'll explain in just a moment. Okay, so statistical multiplexing is the sharing of network bandwidth between the different users according to the statistics of their demand. Now, multiplexing is just the networking word for sharing of a resource. Sharing according to statistics is useful because users are mostly idle, believe it or not, but if you look at your traffic at a fine grain, you're mostly not using the network. And even when you are, the user's traffic is bursty. It occurs in all sorts of little bursts, such that we can typically have many users using the networks together with few ill effects. The key question, though, when we combine many different users onto the one network is how much this helps, how much you can have a different set of users share the network without ill effects. Well, let's work through an example. You can see a figure on the right here shows our setup. We have an ISP which has 100 megabits per second of bandwidth. We haven't talked about megabits per second yet, just think of that as 100 units of bandwidth that it can provide. The ISP is providing service to different users, shown here on the very right. And each user needs 5 megabits per second of bandwidth. They need this amount so they can watch videos or do something like that. But of course, users don't use the network all of the time. In our model, they're active only 50% of the time. Well, the key question here is how many users the ISP can support while providing a reasonable experience to all of them. Imagine that we dedicate bandwidth for every user. Well, in that case, the network will be able to support 100 megabits per second divided by 5, 20 users. Okay, 20 users in a network. However, it's extremely unlikely that all of the 100 megabits per second will be used in this case. Let's work out the probability that all of the bandwidth would be used. Now, for the first user, the probability they're using their bandwidth is 1/2. The second user, the probability they're using their bandwidth is 1/2. Up to the 20th user, the probability they're using their bandwidth is 1/2. Well, that's 1/2 to the 20th power, which is less than 1 in a million. That's tiny. It's very unlikely that we'll use the entire network. What can we do about this? One thing that we can do is add more users to the network. In fact, I've computed ahead of time, so let me tell you that if you have 30 users in this network according to the same assumptions, and all users are using the network independently and randomly, then it's still very unlikely that you'll need more than 100 megabits. I can work out here that it's a 2% chance. How do we work out all of this? Well, the calculation involves binomial probabilities, which you can go and look up if you'd like to find out more about it. The snapshot here on the right shows a binomial calculator where I filled in the parameters. For 30 users, this graph is showing us the probability that a different number of users on the x-axis here will want to use the network. The largest number of users we expect, the number of users which is most likely here is 15. And that is what you would expect given that there are 30 users and they all have a 50% chance of using the network. You can also see the probability that all 30 users are using the network is tiny. Now this would be a half to the 30th power, which is less than 1 in a billion. Similarly, the probability that no one is using the network is also going to be very low. It's also going to be a half to the 30th power, 1 in a billion. Working out whether what the likelihood that 11 users will be using the network or 17 involves the binomial probabilities, for which you can use a calculator. But the key point we can see here is that we expect, mostly we'll have between 10 and 20 users using the network. It's very unlikely we'll have either fewer or more. Given this arrangement, our network can serve more users even though it's the same size. So we get what is called a statistical multiplexing gain here. We're putting 30 users in a network, whereas the bandwidth of the network, if you gave each user their full amount, would support only 20 users. The statistical multiplexing gain here is therefore 30 over 20, or a factor of 1.5. This, by the way, you might have realized is very similar to airline overbooking. Airlines sell more tickets than they have seats on the aircraft because they expect that not everyone will show up. Now, much like airline overbooking, you can get unlucky with statistical multiplexing. More than 20 people may want to use the network. In this case, it may not be as severe as the airline situation, which you just can't get on the plane. All users may have some kind of degraded service, so their video is not so good, but they can still use the network. Another reason that we build networks is to provide efficient content delivery. This became important as the web exploded, where the same content is being delivered to many different users. The content might be web pages, but these days it could also be videos, which are very large, by the way, as well as songs, different kind of applications, operating system and other program upgrades, and so forth. And a key observation here is that we can build content delivery designs so that it is more efficient to use these designs than to send a copy of the information from a source to each individual user separately. We can do this by using replicas in the network. Let me give you an example. Okay, in this example, we want to send a copy of content, whatever it is, from one source to 4 users here. Let's see how we would do that if we send individual copies. Here we are. Let's say we send to the first user, that's 1 message hop, 2 message hops, 3 message hops. And we're going to behave similarly for each user. Send a separate copy through the network. You can see where I'm going here. We took 4 by 3 or 12 network hops in this example to deliver that content. Now let's use replicas in the network. The key replica point is going to be here. So what we will do to deliver the content is send a message from the source to the replica, and then from the replica we will send a copy to each individual user rather than going all the way back to the source. Well, guess what? We just took 4 message hops, 1, 2, 3, 4, and the 2 ones to get from the source to the replica point. That's a total of 6 network hops. It is twice efficient as the 12 network hops that we required in the first case. Another key advantage of networks is for communication between computers, to let computers interact with other computers rather than people communicate with other people. We're doing this when you buy something over the internet, for example, with e-commerce, or perform other kinds of transactions like making a reservation. You may think of these as human-driven, user-driven operations, but think of something like high-frequency trading, where many computers are automatically talking to one another and making decisions. This is increasingly becoming the case. So computer-to-computer communication enables automated information processing across different parties. And yet another emerging usage of computers is to connect the physical world with different computers that are across the network. We can do this by gathering sensor data and actuating devices to manipulate the world. This usage is provided by things such as webcams. Mobile phones are all about gathering sensor data such as location, audio, video, and so forth, and sending it across the network. And here's an example where we manipulate the physical world, a door lock. You can buy automated door locks whereby you can send a message from across the internet and open your front door. This is very much a rich emerging usage that we expect to see more of in the internet. And finally, I want to tell you about the value that's provided by network connectivity. We tend to prefer large networks rather than small networks. They're more valuable because they provide rich connectivity. This is explained by what is called Metcalfe's law, which was postulated by Robert Metcalfe in about 1980. Robert Metcalfe was the inventor of Ethernet. And Metcalfe's law says that the value of a network of size n nodes is proportional to n squared. That might sound a little odd. Let's look at some of the intuition. Here's an example. In both cases, the picture on the left and the picture on the right show networks in which there are 12 nodes. But the left network has much richer connectivity, so it's more valuable in some sense. On the left side, you can see the structure here. Every node in this 12-node network is connected to every other node. That is called a structure called a full mesh. It shows the possible connectivity. On the right-hand side, we have full meshes with 2 nodes of 6 networks. Let's look at the connectivity that you get in this network. On the left side, the number of possible connections from one user to another user are 12 by 11, or 121 different possible connections. On the right side, each network has 6 by 5 possible connections. That's 30, plus another 30. That's 60. Okay, well you can see here that we have much more connectivity on the left side than on the right side. That's the value we get in a large network.